Hi guys, welcome from my now permanent electronics lab here. Got my own space here for working on my faulty devices, which I have plenty of in Thailand in our hot and humid climate. Today we are going to try a really tricky one. You have already recognized it. This is a SUN2000GTIL board. The inverter is really badly damaged from a most probably a lightning surge. And there was also a second inverter involved. You saw it in the last video. It was the SUN2000. That one initially was kind of fixed, but then it developed more and more problems. Later on I even then found out that again most probably the MCU of the anti-islanding circuit was damaged, and this is then again somehow a dead end. That board I have decided is now a donor board. But this one, the SUN2000, we have looked at it in a special video released about 1 month ago, where we did some extra investigation on this AC measurement circuitry, which is responsible for the anti-islanding of this inverter. And as you remember, I have actually written off this inverter more or less already, because we found out that the MCU on this board was shorted. And when you have an MCU, damaged MCU, you don't have many options anymore. So either you get a brand new one from the manufacturer, or you have a donor board with a working one where you can get it. But in this case, I did not have a donor board, so my only option was to ask if I can get a MCU from the manufacturer. And that is what I did. So I contacted my seller of the inverter, and luckily I bought it in China. And where I bought it, that shop was actually the biggest reseller of the Sun inverters. So this is Reassembly official store. And I contacted the support there, told them what was my problem, and the guy said, okay, give me a few days and I will tell you if you can do anything. And he could really get me this MCU. So he also said it's programmed, of course, because the MCU is running a specialized code, and you can of course buy the chip anywhere you want, but you need to program it for this device. And so this should actually be done. So what I did then was removed the MCU, and when you have such a central component which is faulty, then you remove it, then you actually uncover the other layers of faults. And what I found out is that in this circuitry, more or less every single active component, which means diode, transistors, regulators, etc., ICs, was damaged. We will take a look in this in a minute. So the only thing remaining here on this PCB are actually resistors and capacitors. My hope is that I could now remove every single damaged component until the point where there is a certain isolation given to the other parts of the board and the fault is ending there. Right, so I can say that, for example, the control board, which is this one here, is good. This one I know is good because it's from the other SUN2000, because the control board of this damaged inverter is running the other SUN2000 now. So it is working. The other thing, what I don't know yet for sure, but we will find it out, is if there is some short, still some problem, damaged component here in this entry stage here, which goes to our power supply on the board. And so we need to know, of course, if there is a damaged component there, which is then maybe also affecting the power supply. Yeah, this is all because these inverters are unfortunately only powered by AC, and yeah, if you have an AC problem, it's for these inverters, sun inverters, it's like the worst case scenario. This here is the list we will have to do, all the components we will have to replace, and it's as you can see, it's almost unbelievable. We have 8 items on the back side of the board and 29 items on the top side, and this is just what I know until now. So 37 single components need to be replaced on this board to just remove all the damage. And as I said, maybe there will be 1 or 2 more coming from the input stage here, because here are the surge protection varistors here built in, some capacitors, so they could also have had a damage. But this we will just see after the transistors are removed, the MOSFETs or IGBTs, triacs I will also replace on this inverter. That's so far the introduction. The video will for sure not be short, but of course it will be edited so that it is still somehow acceptable by its length, and I have no idea how the probability is of success. We will do this step by step, clear one area, check it. Usually the display and the control board should work, so it will always show us where we are at. And the other thing is why I think that maybe we have a quite good chances for a success is because we are replacing so many components, so almost everything here will be new, and this is of course then better for our chances. So the primary driver for this repair attempt is really the curiosity. Can we get this inverter working again, or even close to it? Does it make sense to repair such a highly damaged device? Well, the components by itself, the costs for this repair will be around $12. That's not so much. I of course had to spend much more because I have now all the parts in the tens, and so I could actually repair 5 inverters of this with the parts which I got. But yeah, $12 is what is going into this. This would of course make sense if you can do it by yourself, but as I said, this is far more damage than usually somebody would try to fix probably. Okay, so we will take a close look now. I will always explain to you also my findings, what this part of the board is doing, and it is a really great piece for me to learn how this AC stage is working, how this measurement and anti-islanding circuitry is controlling this part. So I hope you can also learn a little bit out of this. If you have such a device, if it has a problem on the AC side, you will certainly know much more about it after looking this video. Okay, let's take a look at the damages on the board. We are now at the back side. On the back side we have our shunt resistors. The shunt resistors are 3 milliohm resistors here in a pair to measure voltage drop from the microcontroller, and all these shunt resistors have actually completely broken. When I have removed them, they fell apart, literally. Then we have here another shunt transistor, 1.5 ohms, and a MOSFET. This MOSFET is switching mains power, but I can actually not tell you exactly what it is switching. Anyways, it will be replaced. Then we can see those traces here, which are going from those shunts. The solder mask have peeled off, and also the track was melted and discontinued. So these have to be restored. We will later on have to lay a wire from the new shunt resistors to the measurement circuitry on the other side, and for that I have here drilled a hole where the wires will go through them. On the top we have a missing fuse. We are going to replace the IGBTs or MOSFETs here. I will replace it with a FGP20N60 UFD. This was recommended by a viewer. The original MOSFET, which I think it is, I cannot even find a data sheet for it, unfortunately. Then here we have two triacs. This is a sort of a solid state relay circuit, and those triacs, I got the original ones, will be replaced. Then on the down there, as usual, our gate driver and gate resistor plus pull down resistors. So that's the power circuitry, and the rest of the damage is now all in this area, and this area you can see has already a lot of vacant spaces. All of these have been damaged parts, which is going to be replaced. Let's go through this in detail. If we start here on this area, these are four similar resistors, 360 kilo ohms. They are coming straight from the AC, and yeah, it's more or less a voltage divider, which is breaking the mains voltage down initially, then here divided on the small resistors, and the input will then actually go directly to a MCU pin. And this is also what is showing us the problems already on this inverter. There is basically no isolation between the high mains voltage side and then the low voltage side, which is taking the measurements. So the resistors here have been burned a little bit, and if you would look at the solder mask here, you could also see the color changed to brownish, so we know there was a high current flowing there. Here we have a missing spot. This is the 8 kilohertz oscillator, which is providing frequency for our MCU, and here we have a double diode, two diodes in series, so with a midpoint, and that one was also damaged. Our main vacant spot here, that's the PIC MCU. The problem with the PIC MCU is none of the pins is tolerant to voltages higher than 3.3 volts, and this is then also a problem. If you have a surge coming in from here, the standard voltage on the pins, what I saw, would be somewhere around 2 to 2.5 volts, and now imagine if you have a surge which is double that voltage. There is no Zener diode or anything what would break down an over voltage situation here, and so you would get maybe 4 volts, 4.5 volts into the pin, and that would actually destroy already the MCU. So this here is the path we already discussed in the last video, where the signals from the shunt transistors coming in, two resistors, a double diode with a common cathode, another pull down resistor, and then this is a protective diodes array, which then would also go into the MCU, into a pin. And then everything on this side is newly discovered. Here we have a Zener diode, a signal MOSFET. This is probably switching the triac circuitry, and then we have another Zener diode going here to a optocoupler, and this one will probably drive our gate driver for the MOSFETs or IGBT. So this is a sort of isolation towards that area. Here what's missing is our 3.3 volt voltage regulator, which is taking 12 volts, which is coming from the power supply unit, down to 3.3 volts required by the MCU. And another IC, this IC, this is a 74HC14 Schmidt trigger IC. It is kind of used as a data transfer, because we have that same IC also on the control board here, and they would then transfer signals from one to the other via the flat cable here, right? Here a little bit in general about the input stage. We might expect probably a damage of one of these discs here. These are varistors, which are usually protecting also from surges. So let's see after we clear the transistors there if there is still some short existing. And then in general here about some of the components. This component here, this is a voltage transformer which is sending voltage informations directly to our control board, and this is the voltage which is actually shown in the display, AC voltage. So it does not come from this part, this is just extra provided from here. This here is CT, which is providing the current information. So with voltage and current we then get our power indicated on the display. This here should be our relays for the mechanical anti-islanding protection. Digital is, as I said here, via a solid state relay over the triacs. Our red and black cable here is going to the internal power supply. So this one will then provide 12 volts for the whole board and 3.3 volts for the display and the controller. So it comes from the AC input stage and was of course also subject to the high voltage surge. So let's also just hope that there is no issue with the power supply. The last time I have actually removed all those brackets which were holding these transistors, but this time I have just loosened them, and I think I can just pull the heatsink off the board with all those brackets staying on. So it will surely save me some time, because it's actually not easy to take them off and then put them back on. Yeah, now the heatsink can be removed. And yeah, you see all these clamps here, brackets, actually don't need to be removed. Good, we now have our transistors exposed. So these 4 transistors here will be removed here. Just adding a little bit of solder so it's easier. I'm clipping off the components. It's much easier to remove like that. Okay, so now I have the triacs and the MOSFETs. IGBTs are out. We have here line neutral, and it's showing 99 kilo ohms. And I think, what I remember, this looks normal. Okay, so fortunately, in my opinion, there is no shorted varistor or capacitor. We can now try and power this board up. What I need next is a fuse. So what I will put here is a 15 amps fast blowing fuse. So this is a glass fuse here, and we want to protect this fuse a little bit. So I'm going to cover it in a shrink wrap. The reason for that is that, you know, in case when this fuses, glass fuses blow, that the glass is not kind of flying around here. Okay, put the fuse in here. Solder it in place. Now we can connect this panel so that we can plug in our cable. And then just see what happens. On. I can hear it buzzing, so we do have power on the board. 230 volts here. And let's check if we do have 12 volts on this end. So here's the ground. Here's a 12 volt test point, and we do have 11.74 volts DC, so the power supply is giving us DC voltage, which is great. I will now connect the control board. And we can see if we are getting our 12 volts also here in this area. This here is ground and the input pin of the controller, 12.1 volts. So perfectly we are receiving DC voltage here in our measurement area. This seems to be okay. So what I'm going to do now is removing these other components like the gate driver and the gate resistor, and then we are starting to build up this area again. We do have now the required parts for the power circuit here, IGBTs and the triacs. So these Chinese inverters unfortunately already are using a lot of domestic components which you actually cannot find data sheets for it, and that can be in some cases a little bit tricky because you don't know exactly what it is. I'm going to fit now the gate driver. Good, gate driver is in place. Now the two gate resistors. Gate resistors are in. I will now install the heatsink again, so that there is something holding these transistors before I solder them in place. Okay, I'm starting to rebuild this circuit now. I will start here with the power supply. This is LM1117 for 3.3 volts. Right, the next one is the optocoupler right here. Okay, then I'll add the oscillator there. Okay, now comes the 360 kilo ohm resistors here. I'm going to solder those 1 kilo ohm resistors. I can use what my supplier actually sent to me. They send also those small parts which came before the MCU. One kilo ohm, and here's the MCU, and here's the diodes, and to these 1 kilo ohm resistors then these wires will be attached. And this protection area here in the meantime I am at the Zener diodes at the moment adding an LED. The original LED unfortunately is a 1206 size, but I only have 0805, so yeah, I hope it makes contact. The pads are a little bit too far from each other. Okay, now I have one more of the double diodes, and then only the 2 ICs are left. Place the Schmidt trigger IC first. So the purpose of a Schmidt trigger is usually to improve a signal, because you can make like a square wave out of sine waves, etc. Or when you have a very noisy signal, the Schmidt trigger can clean this out. And it's used in this case a little bit as a data transfer from one panel board to the other one. And this IC was completely shot as well, and it was kind of a isolation device between control board and this part here. Okay, so the only thing missing is now the MCU, which I do not want to put yet. I want to check some signals on the board now first. After I finished populating this measurement circuitry here, I went off camera a little bit because the battery on the camera was already low. My phone did not have storage anymore. I just wanted to actually check and make some measurements here if the voltages are correct or something like this. I powered up the board and I noticed that smoke was coming from the IGBT, And after a while I unfortunately also heard a bang and we had a short again. So I thought, okay, maybe IGBT was not the right thing, changing the resistor there as well. I put the MOSFET inside, the 24 and 60, powered up, and it right away blew up the transistor. But for that try I did not change the gate driver because I only had one left. But now I again checked all the driving circuit, replaced some capacitors, SMD capacitors of the driving circuit from the back side, replaced the transistors again, and now I'm on my last gate driver. I know now more or less every single track which is going where. I know the pins which are going from the MCU to the gate driver, etc. Every component there is checked. Usually nothing should have happened there anyway. There was no MCU on the board, there was no signal to the gate. So why those transistors just blowing up, I don't know. I have then checked all those capacitors, AC capacitors, which are here in combination with the big coils. There's no component I did not check on this board anymore on the AC side. You will now witness the last attempt for this inverter. I will power this up. If it blows up, it will blow up right away anyway, I think. Then I cannot do more than I did. Then the damage somewhere is hidden so deep that I just cannot find out what the problem is with this inverter anymore. Okay, let's just try it. I will just connect these fans here again. Now everything is more or less connected like it should be. Display, everything CT. I will put my magnification glass here a little bit as a protection shield over the MOSFET now, and we just try it, shall we? 3, 2, 1 and power. No bang, no smoke for the time. Now the, oh my god, I had a blinking LED there. We have something on the display, so the display is showing a initial setup. I have a green blinking LED, you won't believe it. Can you see that? Green blinking LED, and green blinking LED means that the AC is okay. On the display I have unfortunately this here, so the inverter does not know at the moment what it is, so we have to try to set this. I have no idea how this works. There is some sort of primary settings here. So the first here is default. I will take that one. And there is something now WIB 100, 200, 300, 500 WL. I have no idea what that means. So I will choose the first one, 100 WL. Then we have here grid inverter 1000G or 2000G. Okay, we take the 2000 of course. Then here is sun wall WDL bed. I have no idea what that means. So now it's bed because I pressed the enter. And here's the voltage range. Okay, we have a 45 to 90 volts that I'm going to choose. So now everything should be set. Save settings, yes. Okay, so we have now a SUN2000, but nothing is happening here. So what can this be? So this is more or less setting the control board. I do not have any information now about power, etc. And I can also not switch around here. Okay, I have researched this a little bit in the internet. I hope we can set this up. Let's see if we will enter that menu again automatically. Oh, interesting. Now it is there. So it just required a restart. Stupidly, I did not try it immediately. But as you can see now, we have a display and we also have voltage. But as I said, the voltage is coming from one component on the board, which is the voltage transformer there. What can we do now? We can actually try to supply the inverter with power. But what I want to do first is set the display to always stay on. Always on at the moment, because yeah, I just don't want to press here 1,000,000 times. Okay, the display will stay on now. We have display, we have voltage, we have starting voltage to low shown here at the moment. That is because there is no DC. So let's connect DC. Here the power supply on the up. Let's power up. I'm going to crank up the amps now slowly so that our capacitors can be slowly charged. So voltage is now up, and you can see in our display starting voltage is now gone, but instead we got grid error. But interestingly, I still have a blinking, green blinking area there, but it's only blinking like once every 30 seconds or so. Good, now we have to find out what the problem is in our grid here, and if we can find it out. But this was already very difficult on the other inverter, on the SUN2000, but that one then stopped working completely. So here, and oh, look at this, did you see that? The grid error disappeared. I've played around a bit, I restarted, and I really don't know what caused the grid error, because now actually everything works fine and it is immediately starting to export. Yeah, so as I said, it's a little bit a mystery at the moment. Anyway, it's getting dark, so for today I can't do anything anymore. I have to put this into the box again and then at some point install it in the power wall to see what it is in general doing, how much power we can get out of it. But as you can see, AC DC exporting here 200 watts, no problem. I just don't want to go so high now because there is no heatsink there for the diodes for the DC side. Okay, so this is the end of day one. I will finish this up tomorrow and then we are going to edit this to one video. Good morning again. It is day 2 in our SUN2000 SUN2000GTIL repair. And so yesterday we ended up with a running inverter, and it did export to the grid, at least what was supplied by the power supply here. But before I'm going to assemble this device again, we have to still do something. I promised you we are going to look into the signals here of this AC part. For that I have my small handheld oscilloscope, and I also have prepared a list. This is the microcontroller, the pins, and where on which pin something is happening here. And yeah, this I want to show you. So if at some point one day you have the same issue, then you can also take a look by yourself. But of course, especially when we are looking later into the gate drive signals, for this unfortunately you need a two-channel oscilloscope, because you need to see if those two gates are correctly driven. There must be a time delay between the two driving signals from one side to the other. So it's always one MOSFET or IGBT is responsible for one half of the sine wave, and of course they are not allowed to be driven at the same time at any point of time. So, but this unfortunately I can only look at with a two-channel oscilloscope. Oscilloscope is on my list, wish list of course, and yeah, I will have to save some money for it, but the next tool will be a better oscilloscope. Right, so let's take a look into this circuitry and let's see what the oscilloscope is showing us, how big the signals are, how they're looking like, and what the problems can be in a circuit like this when you have an AC surge. Why this circuitry is not withstanding such surges. Let's power up the inverter. AC. And DC, we have green blinking, very nice. I want to set the output of the inverter to somewhere around 50 watts. Always when you probe something in mains voltage, even if you are now in the low voltage signal area, always use your probe with a 10-time factor. I have set the voltages here at 0.2 volts per division, so that means 2 volts per division with our 10 times probe. So the first thing I want to see is the AC input. We have a probe point here for the line, and you can see we have a half wave here, and it's about 2 volts from a peak to 0. The neutral is similar, so this is the other half wave, and this is going into pin 2 and 4 here of the MCU. I'm not going to probe the pins because they're too close together. I don't want to shorten out something. Let's look at the MOSFET gate drive. This is here on pin 26 and 24 are the two gate driving pins, and these here are the two resistors, pull down resistors for them. So if I'm probing here one, you can see we have a nice square wave there, one and the other one. So if we would have now a two-channel oscilloscope, we could see if those can align nicely here, and that we have a small gap in between. Okay, then at pin 27 we have an output which is going to the signal MOSFET and then going to the optocoupler here also, and probably also to the optocoupler here from the triac, and this optocoupler here seems to go to the relay. So those are switched by the same pin. The anti-islanding pin is this, so it will then set the inverter on or off when the AC is available or not. So we can test this one here at the signal, at the gate of the signal MOSFET. It must be, of course, now on or off. So it's just, you see, this DC signal. So another pin which I know is the pin 22. Pin 22 is the LED pin here. We should be able to see the blinking LED. And here we can see 2 seconds per blink interval. So then the pin 20, it is here also marked as a probe point. This one is just on or off. This is given to the control board as a signal when the AC is okay or not. So the control board will then interpret it as a sort of frequency. When the signal is off, then the control board will write 46.1 Hertz is only available and give us a grid error. But it's essentially only an on or off signal from the microcontroller to the control board. On the other side, the pin 6, that is coming from our shunt, AC shunt. Yeah, this is also just a voltage signal, a voltage level, nothing else. Yeah, those were the signals and the respective pins. I will show you this at the end of the video, right? The list of components which I have used, and these findings, which pin is what on the microcontroller. I'm going to assemble this now so that we can then later on install it in the Powerwall and then see how this inverter is behaving in a real-time scenario. The inverter is back in one piece. Let's take a last peek what we have done. We have worked mostly in this area. There in the back you can see the 2 wires which are coming from the back side of the panel, from the shunt. Resistors. What I didn't show yet yesterday before the last try, so after I have replaced the transistors last time again, I have removed all these caps here, especially the big one. And this one's here also on this side. I also removed them on the SUN2000 on my donor board, and then I took the 2 most similar by measurement of these 2 big capacitors and put it in place. They have been quite different in the capacitance, and yeah, so by using the most similar ones, this circuitry here, switching circuitry, should actually work the best. Let's recap a little bit. The inverter is outputting now maximum what I can give him here with the power supply, 220 watts. AC faults on these SUN inverters. It is the absolute nightmare. It is the worst case scenario you can have, because there will be always a lot of damage. So if you have just a short by some reason, you have to expect the gate driving circuit being affected. You need a new gate driver, you need resistances. There's also the path between my MCU and the gate driver. There are 4 components on the back side, I didn't show it to you. 2 100 ohm resistors and 2 small SMD capacitors. I replaced those with the smallest value I had, which was 220 picofarad. I think the original value is smaller than that. After I more or less replaced every single component of the gate driving circuit, it seems to work now, at least like always when we did the repair until now, with around 200 watts. But surges seem to have horrible effects on these devices, because the surges can go into the anti-islanding measurement driving circuitry there. That MCU is responsible for gate driving and all the switching of the safety features here of the inverter. And if you get a surge on any of those pins, you may have easily a defect pin. You need a programmed MCU. However you then achieve this task, I got mine from the manufacturer. Otherwise you have no chance to repair this sort of failure. So anytime when you get an AC failure and then maybe this is ending up in a grid error message. Grid error message does not mean that the MCU is damaged. The MCU still can provide its information to the control board, but that does also not mean that none of the pins is affected. It could be one pin which is burned out and this is not working anymore. What kind of advice can I give you if you have a device like this with an AC fault? Very, very tricky. If you wanna try a repair, you should really expect the worst, and you will have to contact your seller to get most probably the MCU. That's kind of it. Let's see how this one will then show inside the Powerwall in the evening, and then the video will end with the final conclusions. The inverter is now inside the Powerwall. It will in any moment start inverting. But I noticed something. When I had the inverter connected at the workplace, it perfectly showed 230 volts. Then I brought it here, connected it, and it only showed somewhere around 200 volts. Now it went up to 250. So I think there is an issue with the voltage reading. So that is not coming from the area which I told you. It is coming from a separate component in the entry stage and going directly to the control board. So either there's an issue with that component, or we have an issue maybe with something on the control board. Let's wait until the inverter gets the DC from the Powerwall, and then we'll see what happens. I have set the inverter to output 1000 watts, and I've unfortunately noticed something else. So my meter in the Powerwall actually says that the demand on this phase at the moment is 1800 watts, and here the CT is only showing 540. Slowly I'm getting, okay, DC has just turned on. Okay, so did you just see that it did not even reach 80 watts? Now it's trying again. 620 watts on the CT. Yeah, okay, so there are far bigger issues at the moment. I'll set the output for the time to somewhere really low. No. So okay, this inverter has still quite some issues. So the voltage readout is absolutely false. The CT readout seems to be false, at least at the moment. You see, it's quite strange. So when it starts to ramp up, the CT value readout will immediately drop down to 0, and maybe even that's why. And now when it tries to ramp up, it shows like 500 watts, but in reality there's much more demand on this phase yet, so it is absolutely not working at the moment. Okay guys, I just turned off the camera to see if I can change some of the basic settings, you know, this initial menu there. And before I could even do anything, there was again a big bang. The inverter flew around my ears. It was essentially just idling now. Same it did for hours in my new workspace there. So yeah, that was it. The AC side fault challenge is over. There's nothing to do. I can't really get anything out of this. I have no clue what is making these transistors blowing up. The transistor which is now inside there can handle 24 amps and up to 240 watts of power dissipation. So there should be absolutely no issue during idling. This can only be a gate driving issue, but the gate driver, everything, as you know, there's nothing more I can do there because everything is brand new anyway. Yeah, that's it. I don't have any gate drivers anyway anymore. It's just not working. I will put the other SUN2000 back there. I'm happy if it can output 500 watts without blowing itself up. It's still better than I don't have an inverter hanging here. Yeah, sorry, it was a long video, but yeah, it was, as I said, for the exercise, for the curiosity, for the fun. The SUN inverters, they don't like me here too much. One day, of course, there will be a different solution for this because, of course, I'm not going to replace them anymore in future. Okay, so that was it. Again, an unfortunate end. But still, I hope you enjoyed the video. If you liked it, please give me a thumbs up. Thank you for watching and subscribe to the channel. I see you next time.